Lesson 7, activities. If f goes from increasing to decreasing at a point, then the point is a relative or local max. If f goes from decreasing to increasing, then the point is a relative or local min. This is just another way to say the last theorem from the demo today. Number 2, let's find the absolute extrema of this function on the interval -1 to 2.5. Standard calculus question with a standard calculus process. So we take the derivative. This will find us our critical points. 3x squared minus 8x plus 4. We set it equal to 0. I could use the quadratic formula. I'm guessing this one factors. Let's see. We're looking for a 4 and an 8. But 2 here and a 2 here. I think that'll do it. Yeah, that looks good to me. Set each piece equal to 0. Solve for x. 2/3 here, 2 here. Those are the critical points. We'll make our chart x and not f prime, but f. That's what goes into the table. And we're going to put our critical points up here, 2/3 and 2. And you also put into the chart your endpoints, which are -1 and 2.5. And last thing before we plug in is make sure that the critical points are indeed in the interval. 2/3, yep, that's in between, and so is 2. So we're doing 4 function calls here. I'm going to use my calculator to save on the grunt work. And I think the best bet is to type the original function right in here. X to the 3rd, that's too many, minus 4x squared plus 4x plus 2. Okay, and then set your independent variable to ask. And then second table. And so we'll just type in the numbers 2 divided by 3 and 2 and -1 and 2.5. So we got 3.18 to -7, one more, 2.625. So for the absolute min, we're just looking for the lowest y value anywhere. That's the -7. So -1, -7. And then the absolute max is the highest y value anywhere. That's this one at the top. 2/3, and I'm guessing this 3.18 is an approximation. So those are the absolute extrema of this function. You can check the work on the graphing calculator if you want to see, just verify that those are indeed the right numbers. Oh, I'll just do it. It's so darn satisfying to make a tight window. I'm sure you agree. All right, here we go. Window. So we're going to go from -1 to 2.5. And then the minimum is at -7. And then the maximum is this 3.18, but it's like 3.18 and change. So I'll call it 3.19 just to be safe. And we should see this graph. Like you can see, it starts at the bottom left corner. It maxes out, bounces magically right at the top. We knew exactly where that was going to happen. And so indeed, the maximum is right here at 2/3 and then 3.18. The other critical point was over here at 2, but it's not an absolute max or an absolute min. And then -1, -7 is artificially the absolute min. And then this guy right here is pretty high at 2.5, but not quite as high as 3.18. B, find the critical numbers and use the first derivative test to determine whether they're maxes or mins, and then we'll justify. Okay, critical numbers means take a derivative first. 3x squared minus 27. Set it equal to 0. In this case, we don't ignore the -3. This is not an in-context problem. So those are our critical numbers. There are no other critical numbers because there's no place where this derivative is undefined. It's defined everywhere. Okay, and so we're going to do our sign test. I've got -3, I've got +3, and there should be no other numbers on that number line. Do not put 0 in there. It's just going to make it confusing. just the critical points, and that is all. And we're going to label this thing with the function that the -3 and 3 came from, which was not g, it was g prime. That's where it came from. And then we're going to pick numbers that are inside of these intervals, less than -3, between -3 and 3, and then bigger than 3. Okay, let's pick a number out here. I choose -100 for x. So we're plugging into the derivative now, plugging -100 right there. So we're doing this mentally. -100 squared becomes positive, something really big. Then we triple it, and then we subtract the puny 27. And at the end of the day, it's going to be positive. Now we'll pick a number in between. I'll pick 0. This one should be pretty easy. Plug 0 there. I get 3 times nothing minus 27. That's -27. I just record the negative. And then finally, we'll pick a number out here. I choose x equals 100. 100 squared is big. Triple that, it's bigger. Subtract puny 27, and it's still going to be positive. And so that means that the original function f is increasing, and then decreasing, and then increasing, which tells me that f has a maximum right there, and a minimum right there, relative or local maxes and mins. Okay, so we'll fill in the blanks to justify. So g prime goes from, let's do the first one, it was positive to negative at x equals -3, therefore g has a local max at the same x equals -3. And now we'll fill in the other one. Since g prime goes from negative to positive at x equals 3, g has a local min at x equals 3. Okay, 3, optimization problems combine mathematical modeling, which is translating a problem into a function with a known formula, with finding global minima and maxima. The key is to understand the function being optimized by looking at the situation in the problem and eliminating all but one variable, and then find critical points and endpoints. So basic strategy you can read through on your own. You've got that there as a guide, but we're just going to jump into number 5. So we've got a rectangular box that we're putting into the mail. There's just a square box. Assuming width and height are equal. Okay, so this is a square box where the width and the height are equal. So we're going to say it's like a square here on this end, and then another square here on this end. And then we're going to connect. That is no good. Let's try that again. All right, you know what? I failed with my second box. Let's move this one off center more. Okay, so we're going to connect here. We're connect here. And then this one, and then this other one, we can't see, it's behind. All right, not too bad. Okay, so it says that the width and the height are equal, so I guess we can call this one h for height, and we might as well call this one h for width, but they're equal. And then I think an L for length looks good. We'll define our variables. Let h equal the height in inches, and then L equals length in inches. Okay, so it says that we're allowed to have a length plus a girth no more than 108 inches. So that's an equation we're going to write down. Length plus the girth, we got to read what girth means, no more than 108. Let me change this. So it's less than or equal to 108. Okay, and it says the girth is the perimeter of a cross section. So a cross section, so ignoring the L dimension, but a cross section is this kind of thing here. Right, that's a cross section, and the perimeter of that cross section, well, it's h's all around, right? So the perimeter is 4h. So that's an inequality that must be true. L plus 4h has to be less than or equal to 108, and we're trying to maximize the volume of the box that we can mail subject to that constraint, that 108 constraint. Okay, so the volume of the box we know is length times width times height. But there's no W in this one, it's H for both. So L times H squared, groovy. But it's no good to have two variables on the right-hand side of this equation. We need to get it down to a single variable. That's where we use that constraint that's written up there. Now, we're not going to have a lot of experience dealing with inequality constraints, so we're just going to say that instead of doing a less than, we're going to make it equal. Because if you chose to use less, like let's say you made a box with a length plus a girth of 107, well, I could make one of those dimensions a tiny bit bigger, which would make the box a tiny bit bigger, and use all 108 inches available to me. So clearly the biggest, absolute biggest box is going to happen when you use up all 108 available inches. So we can take this equation and solve it for either L or H. I'm going to solve for, what are we going to solve for? Let's solve for L. Doesn't make any difference, but let's solve for L. So L is equal to 108 minus 4H. And that is what we're going to substitute into our volume equation. So instead of L times H squared, it becomes 108 minus 4H times H squared. Okay, and we are trying to maximize the volume, which means take a derivative of that volume equation. But I can't yet because it's a product, and so I need to rewrite this by distributing. So this becomes 108H squared minus 4H cubed. Now I can take a derivative. So good notation, V prime equals, the 2 comes down, doubles the 108, 216H minus the 3 comes down, multiplies by the 4 to give 12H to the second. So that's the derivative. I'm interested in taking the derivative and setting it equal to 0. That's going to find me candidates for places where this thing is max or min. So we set it equal to 0, and then we solve for H. So in this case, I think factoring out is the best bet. So let's go ahead and factor out, so we can factor out an H from both of these, and we can factor out some of the numerical part as well. Does 12 go into 216? You'd think I would know these things, right? Okay, so 216 divided by 12. No whammies, no whammies. Hey. Okay, so 12 is the greatest common factor, and it goes in 18 times. So 12H comes outside, 18 minus H. That's looking pretty good. And then we take each piece and set it equal to 0. So 12H equals 0, that's 1. And then 18 minus H equals 0, that'll be the other equation. H equals 0, that sounds fishy to me, but maybe. And then H equals 18 over here. I guess I would add H to both sides. So those are our critical points. But the question is H equals 0 okay? Well, remember H is the height of this box. And if you have no height, you have no box. So we're going to reject that one. Sorry. So the only critical point in play for us is H equals 18. So we're going to make our sign chart. We're going to put 18 over here. We're going to put the function that this thing came from. This was a V prime. And then we're going to put 0 here. And I'm making very clear 0 is the end. 0 is no good. Anything negative is no good. And then we're plugging, we're going to do our sign test. We're pick number in here, pick a number in here, plug into V prime and record the sign. So here we go. V prime, we got a couple of versions of V prime. You could use this version or this version. Either way is okay with me. If I have a factored thing, I'm probably using it. So let us use the factored version. We're picking a number that is in between 0 and 18, for example, 10. And I'm plugging 10 in for both H's. So 10 right here, 12 times 10. Don't do the arithmetic, but just note that is a positive thing. 10 right here. 18 minus 10 is also a positive thing. And I multiply these two positive things and I get a positive thing. Now we're picking a number out here. How about 100? So plugging into this again, H is 100, this is positive. H is 100, 18 minus 100 is negative. So I had a plus times a minus, and that is a minus. And so we just got information about V prime. But if I'm interested in drawing the graph of V, I would say V is increasing and then V is decreasing. And so lo and behold, at 18, we have a max. Hey, that's exactly what we wanted. Okay, so let's make sure we answer the questions. We know we've got our winning H, but let's be clear what we're trying to find. It says find the dimensions of the box and also find the maximum volume. Okay, great. So we calculated that the best h is 18. The width is also 18. The length, so let's go to the one equation that says L equals. Where is it? Right there on the top right in red, 108 minus 4h. That's what we're putting. 108 minus 4h. 108 minus 4 times the height we discovered was 18. 108 minus 72, is that 36? That sounds good to me. And then it also asked for the maximum volume. And the volume is just the length times the width times the height. So 36 times 18 times 18. (36 times 18 times 18), 11,664. And I guess that's cubic inches. That is the biggest volume to box you can do given the 108-inch constraint. Okay, let's write our sentence. There's no blanks here, but we're going to follow the same format as before. Since V prime goes from positive to negative at h equals 18, V has a max at h equals 18. Now the fact is, the sign test only tells you that it is a local max. However, looking at the fact that there are no other critical points anywhere, right? 18 was the only one that was in play, that this function goes up forever to the left and it goes down forever to the right. And so that makes 18 the absolute max. Absolute max.